today is 6.5b. And yesterday in 6.5a, we saw this for the first time. dy dx equals ky times m minus y. So that was the first time we'd seen this type of a differential equation. And we learned that the curve that you get from this after you solve for y is called the logistic curve. And the logistic curve looks like this. So we saw this differential equation for the first time. We learned that if you solve for y, it'll end up looking like this. And that curve is called the logistic curve. What we didn't find out yesterday was what the equation for this logistic curve was. And remember I said we were going to wait till today to do it because it's a logistical nightmare to solve it. So if you missed that joke, I wanted to make sure you were in on it today. All right, so that's what we're going to do in example 1. And in this problem, P represents population, and it's actually wolf population. And T is in months. So T is time in months. And the differential equation that we're given is dP dt equals 0.0008 p times 700 minus p. And we're also given the 0.010. Okay, so just to kind of solidify what's going on, what does the 0, 10 mean? It's a point on the graph. It helps you find C. Okay, now in this context, what does it mean? After 0 months have gone by, there's 10 wolves in the population. So right at the start of the problem, at time t equals 0, there's 10 wolves. Okay, then looking at this differential equation, what is the k? 0.0008, and what's the m? 700. So for a particular problem, the k and the m are going to be numbers, and the y, of course, is a variable. All right, so now what we want to do is solve this. And solve means figure out the original equation. In this case, the variable is p, so we're solving for p. We can't take the antiderivative straight up because there's p's in our differential equation, so we have to separate the variables. So first we're going to multiply the dt to the other side. Then we're going to divide the p, and at the same time we're also going to divide the 700 minus p. So that's going to be 1 over p times 700 minus p dp equals 0.0008 dt. So that step was just separating the variables, getting all the p's on the left and all the t's on the right. So after you do that, then you can take the antiderivative of both sides. The antiderivative of the right side is pretty easy. So we'll deal with that in a second. This antiderivative is tough. When we have tough antiderivatives, we have two tools now. The first one was U substitution. The second one was partial fractions. So we learned partial fractions yesterday. And that's what we're going to have to do on this problem to take the antiderivative. So apparently I can take this fraction and split it up into two fractions. So now I'm going to go off to the side and work on just that, taking this mess and writing it as two separate fractions. All right, so I think that we can put A over P plus B over 700 minus P. And I apparently what we're trying to do is figure out what these two fractions would be to add up to be what we have. So in order to do that, we're going to get a common denominator. The common denominator would be p times 700 minus p. I need to multiply this one by 700 minus p over 700 minus p. So that'll be a times 700 minus p all over p times 700 minus p. So that was just getting the common denominator for the first fraction. And then for the second fraction, I'm going to multiply by p over p. So that'll give me bp over p times 700 minus p. So now that I have a common denominator, I can add the fractions. So, and at the same time, I'm going to distribute this a. So that'll say 700a minus ap. This is why this is called an AP class, just because this was going to come up today. No other reason. So we got 700a minus ap plus bp. That would be the numerator of the new fraction, right? And then the denominator would be p times 700 minus p. What do I need the numerator to come out to? I need it to come out to 1, right? So I need that numerator to equal 1. It's kind of easy to forget what's the variable here. P is the variable. A and B are numbers. So that means I would combine those terms, the negative AP and the BP. And there aren't any P's over here, right? So that means that those need to add up to be 0. So negative A plus B needs to equal 0. So I think there was one like that on the homework, and that might have thrown you off. But I knew it was going to come up today, so there it is. If you don't have any P's or you don't have any X's, then they need to add up to 0. Okay, then this is our only constant term, so that needs to be 1. So my other equation is 700a equals 1. Then that's easy to solve. You just divide both sides by 700. So a is 1/700th. And then we can plug into here to figure out b. So negative 1/700th plus b is 0. So then adding 1/700th to the other side, b is also 1/700th. That doesn't happen very often, but on this problem, the a and the b are the same number. Okay, so that means that this number could be 1/700th over p plus 1/700th over this. Apparently those two fractions will add up to be this thing right here in the middle. So I'm trying to take the antiderivative of that. So instead, I'm going to take the antiderivative of what I just figured out. Okay, so I've got the antiderivative of 1/700th over p plus 1/700th over 700 minus p dp equals the antiderivative 0.008 dt. So all I did from that step to this step is split the fraction up into two separate fractions. And all that work over there was to figure out what the two separate fractions should be. That's called partial fraction decomposition. Okay, now the reason I did that is I didn't know how to take the antiderivative of that mess, but it's easier to take the antiderivative of these. The way you do that is you do them separately. When you have a plus sign, you can do the antiderivative of the first thing plus the antiderivative of the second thing. Okay, so let's look at this antiderivative. The 1/700th could come in front, and then it would be 1 over p, right? And then the antiderivative of 1 over p is the natural log. So we have 1/700th, that came out front, times the natural log of the absolute value of p. So this is the antiderivative of that. Everybody okay with that antiderivative? Okay, now for this one, the 1/700th could come out in front as well. And then, does natural log come into play for this one? It does, because it's still p to the first power, right? Anytime you have a p to the first power in the denominator, natural log comes into play. Or a y, or whatever it is. Now, if it was squared or cubed or negative or anything, no. But since it's p to the first. Okay, so I'm going to write down the antiderivative, but this isn't exactly right. Since it's 1 over 700 minus p, it's going to be the natural log of 700 minus p. But why isn't this exactly right? Yeah, Kasha. Because there's chain rule, right? If you took the derivative of this mass, you would get 1 over 700 minus p. But then you'd also have to take the derivative of the inside, the 700 minus p. So if you do that, it's 0 minus 1. So the derivative of the inside is negative 1. So that's messing with the final answer because an extra negative 1 would pop out if we took the derivative of this. But we can compensate for that by dividing by that extra negative 1. So I just did a u substitution in my head, right? Like if there was a 2p in there, we would divide by 2. The u substitution in the head is okay because it's a really easy inside derivative. All right, so is everybody okay with this antiderivative now? All right, then the other side is easy, right? It's just 0.0008t. The antiderivative constant is just that times t. All right, now I'm going to multiply both sides by 700 to get rid of the 1/700. So natural log of the absolute value of p minus, because of that, right? Natural log of the absolute value, 700 minus p, equals, so I'm multiplying every term by 700 to clear the 700. Now, so I got to take 0.0008 times 700. That comes out to 0.56. You have to multiply the c by 700 also. But to make things simpler, I'm going to call this up here C1. And then whatever 700 times that is going to be my new C. So instead of writing plus 700C, I can just write plus C. This C is different than that C. But it doesn't matter because it just represents a constant. Okay, now what can I do with 2 logs subtracted? I can combine it into 1 log and divide, right? So I've got the natural log of the absolute value of p divided by the absolute value of 700 minus p equals 0.56t plus c. Yes.
How do you know that, like, when you did the A plus B, that the P was under the A and not under the B? Because wouldn't you not have it flip? So it would be 700 minus P over Q for when you go to subtract it?
Yeah, I mean, unfortunately, I just erased it, but when I put A down, it was over P.
Right. How do you know it's not B is over P, though?
Well, A just represents a number, so when you set it up, if you write A over P, then you're deciding right then that the A is over the P. And then when you write B over 700 minus P, you're deciding that the B is over the 700 minus P.
I just wouldn't have it flip, though, like, if you, because when you go to add them later.
The subtraction came from the antiderivative.
Okay.
Plus, it doesn't matter if they're flipped, because it's plus. Plus, in this case, the a and the b are the same numbers, so it doesn't really matter which one's a and which one's b. But the real answer to your question is, I could have put c over p plus d over 700 minus p. And it doesn't matter what I call the number. I'm just deciding that a number is going to be over p, and I'm calling it a. Good. Is everybody okay with this? All right, now what does P represent? Population, right? Wolf population. So P could never be negative because it's population. So I'm going to get rid of these absolute value symbols around P. And then also, I'm going to show you this later. You have to take my word for it right now. The population is never going to be bigger than 700. So because of that, I don't know why I have a parenthesis there. I should have an absolute value there, right? Because of that, since P is never bigger than 700, it's going to be only like 600, this is going to be a positive number as well. So I can get rid of these absolute values. I'm going to tell you why those absolute values can go away later. For now, you just have to take my word for it, that P is not going to be bigger than 700. Okay, so that makes it simpler because now I don't have to deal with the absolute values. All right, so now how do I get rid of natural log? E to the power, right? So now I'm going to raise up both sides from E. So that's going to give me P over 700 minus P equals E to the 0.56 T times E to the C. Now I'm going to flip both sides. So I'm going to write 700 minus P over P equals 1 over E to the 0.56 T times E to the C. So from this step to this step, I just flipped both sides of the fractions. Now you might be wondering why I did that. The reason I did that is because now this P can distribute. I can take the 700 divided by P and the P divided by P. I can't do that when it's like that. And the nice thing about that is then the P divided by P is going to be 1. So I've got 700 over P minus 1 now on that side. And then I'm just going to rewrite this side. Isn't 1 over an exponent? Couldn't that be written as the negative exponent? So this is e to the negative 0.56 t times e to the negative c. I just moved both of these terms upstairs, and then that's why they became negative. Now I'm going to add the 1. So 700 over P equals e to the negative 0.56 t times e to the negative c plus 1. Now I'm going to flip again to get this P back upstairs. So I'm going to flip both sides, reciprocal both sides. So that's P over 700 equals 1 over e to the negative 0.56 t times e to the negative c plus 1. I can't change those negative exponents to positive because the plus 1 messes that up, if that's what you're thinking, Rebecca. Yeah. Everybody doing okay? Now I just have to multiply by 700 and I've got p. I was trying to solve for p, right? So p equals 700 over. I'm also going to swap this plus, because this is usually the way we write it is 1 plus, and the e to the negative c is usually in front. So now I have to get rid of c. How do I get rid of c? I have the point 0, 10, right? That was given in the original problem. So if I plug a 0 in for t, so I'm just taking this, plugging a 0 in for t. I know I'm supposed to get 10 out. .56 times 0 is 0. E to the 0 is 1. So this is 10 equals 700 over 1 plus e to the negative c. Yes?
I'm a little confused. Like, when you've got the 700 over e to the negative exponent, is it supposed to be like you have, I would just think that it would be a positive on the bottom, wouldn't it? A positive exponent for like negative 0.56. Why is it negative on the negative exponent?
So it was negative here, and I flipped it. So it's 1 over that. So I had 700 over p, and I wanted to have p over 700.
Oh.
So I reciprocaled this side, and so then I had to reciprocal that other side as well. So it's 1 over that whole mess. Now, it would be really nice if 1 over that whole mess became a positive exponent, but that doesn't work out because the plus 1, if it was just 1 over that, then yes, you could make it positive. But the plus 1, it just doesn't work out that way. So that's why we're stuck with the negative in the denominator. Great question. Everybody good to this stage now? Okay, now I'm going to flip both sides again. So 1/10 equals 1 plus e to the negative c over 700. Because I'm trying to solve for e to the negative c now. Now I'm going to multiply 700 times 1/10 to clear that. That's 70. And then I'm going to subtract 1. So that tells me that e to the negative c is 69. All right, so now I have a nice solid final answer. That was e to the negative c sitting right there, right? I just found out that this whole equation is my final answer. Okay, so that was a pain, but here's what we just found out. We just found out that when you have a curve, a differential equation like this, it's the logistical curve, it's the logistic curve. When you solve, and that means it's going to look like this. But every time when you solve this kind of a differential equation, it's going to turn out like this. Y equals m over 1 plus a times e to the negative mkt. let's just check that that's the case in this problem. What was the m? Look back at the original differential equation. The m was 700, right? Because it said 700 minus p. Did we end up with m on top in our final answer? Yes, we did. Okay, what was the k? 0.0008, right? If you take 0.008 times m times 700, do you get the 0.56? And is it negative? Yeah, so that's checking out. So on a lot of these problems for homework, you're just going to go directly from here to here. You won't have to go through all that nastiness. Now, I will say this. For AB students, I want you to do that nastiness once on the homework, okay? And BC students, I want you to do it twice. But then on all the other problems, if you have a curve that looks like this, you can just go straight to here. So you won't have to go through all the separation of variables every time. Yes?
Where do we find the A?
That from the initial value. So the A was this, right? And so we had to plug the 0 and the 10 in to get it. And people usually say, well, what does that mean? It doesn't really have any meaning. It's just a constant that you'll find from the 0, 10, or whatever initial value they give you. Yeah?
So the A does not relate at all to the partial fraction decomposition?
Yeah, this is as far as we got. Sorry. That's as far as we got with the partial fractions. And then we just had to figure out that number from the 0, 10 that they gave us.
Okay.
So it's just like any other antiderivative problem. You need a starting value, a 0, 10, or a 0, whatever, to find out the C. Yes. Okay, so that was part A. Part B is not nearly as hard. So for part B, the question is find the carrying capacity. And I need to explain, obviously, what carrying capacity is. So in our example, we have the population, the wolf population, and the wolves live, let's say, in a forest. And so the forest is their ecosystem. And that ecosystem only has a certain amount of food and shelter and water. So because of that, the wolf population can't get really, really big because there wouldn't be enough food for all of them. So the carrying capacity is the wolf population that the ecosystem can sustain. The population that an ecosystem can sustain. That's what carrying capacity is. Okay, now what happens is we started with 10 wolves, right, because it was 0, 10. So we started with 10 wolves, and at first there's lots and lots of extra water, there's lots and lots of extra food, so the wolf population really grows. But then as time goes by, there's going to be less food, and so it won't grow as much. And so as time goes by, the population approaches the carrying capacity. As time goes by, the population approaches the carrying capacity. So what I'm saying is, if you want to find the carrying capacity, you just take the limit of the population and see what it gets closer and closer to as the time goes by. All right, so that's going to be, in this case, the limit as t goes to infinity of 700 over 1 plus 69 e to the negative 0.56 t. There's our population equation that we figured out in part A, right? And if we take the limit of that, that's going to give us our carrying capacity. So the biological definition of carrying capacity is the population that the ecosystem can sustain. But the fact is that, as time goes by, the population is going to approach that. Sorry.
That's okay. I just had a quick question. When would be a good time to come back and try and install path cutting?
Any time is fine.
Okay, so-
Yeah,
okay.
it doesn't bother me.
Okay.
Yeah.
Just wanted to be sure.
Yeah, thank you for checking.
No problem.
All right, so if we figure out this limit, that's going to give us our carrying capacity, right? Okay, so now to figure out this limit, well, limit laws say we can do the limit of the top separate from the limit of the bottom, right? As long as the bottom doesn't come out to 0. Okay, so the limit of the top is 700, because the limit of a constant is just a constant. Okay, now we're doing the limit of two things added. There's another limit law that says you can do the limit of the first thing plus the limit of the second thing. So we're just going to do the limit of 1, which is 1. Now we've got the limit of this, 69e to the negative 0.56t. There's a theorem that says you can bring the constant out in front of the limit. So really, we're just taking 69 times the limit as t goes to infinity of e to the negative 0.56t. So I did a bunch of limit laws to get to this point, right? It's been a long time since we talked about limit laws. Okay, so then that is 700 all over 1 plus 69 times e to the negative 0.56t could be written as 1 over e to the 0.56t, right? So we're taking the limit as t goes to infinity of 1 over e to the positive 0.56t. So now we're plugging a really big number in there for t, right? 0.56 times a really big number is a really big number. E to the power of a really big number is a really big number. So we're taking 1 divided by a really big number. What's that getting close to? Getting close to 0. So we got 700. So I guess I'll start going this way now since I'm running out of space. 700 all over 1 plus 69 times 0. 69 times 0 is 0. 1 plus 0 is 1. 700 divided by 1 is 700. So that means the carrying capacity is 700. And George is also noticing that that's M. I want you to go through this. I don't want you to just write down, oh, it's M, I see it, because it'll help you realize what's going on. But yes, that's how you check your answer. Okay, now, this is going back to week 2 as well. When you take the limit as t goes to infinity of the y value, what are you finding?
Quick question.
Yes. No, sorry, I don't have time. After class. When you take the limit as x goes to infinity of f of x, what are you finding? Nice try. You're finding the horizontal asymptotes. And doesn't the logistic curve have a horizontal asymptote? So apparently for this problem, that's at 700. And the population is getting closer and closer to that. So that's 3 ideas about what the carrying capacity is. There's the biological definition, there's the mathematical definition, and then that's the horizontal asymptote. Okay, just one other thing I need to say. There's a couple of problems that are maximum problems. So that's review from... So let's say we wanted to find the maximum population. What would we do to find the maximum population? Take the derivative of the population formula and set it equal to 0 and undefined, right? We already have the derivative. Okay, what if you wanted the maximum rate? Take the derivative of that, the rate function, and set it equal to 0, right? So that's review, but it's a little confusing, so I wanted to remind you about it. Thank you for your patience. I really appreciate it.
That was my question.